Hello, y'all, and welcome to lesson 46, structure 2.2.8, part 2. So we're still going over the nature of the forces that exist between molecules, specifically intermolecular forces. And as this is part 2, we're covering only hydrogen bonding. We'll talk about the specific situations in which hydrogen bonding occurs. So hydrogen bonds, or H bonds, exist in a variety of things, and they exist a lot in nature. So let's start with just a little bit of a background. We have this chart right here, which shows the boiling point of various molecules when they convert from a liquid phase to a gaseous phase. And they're all hydrogen 2 and something else, so H2X. If we look at period 2, we have H2O. Period 3, we have H2S, H2SE, and H2TE in period 5. And if we look at the boiling points of them, we notice a couple things. First, we notice a steady increase, almost linear between periods 3 through 5. And we can see that while they all have very similar electronegativities, and we know that intermolecular forces are what accounts for things like boiling and phase changes, we can probably assume this is due to London dispersion forces, which we talked about in the previous video. As the elements have more electrons, as in tellurium or selenium, as opposed to sulfur, these elements exhibit stronger London dispersion forces, and all their dipole moments are pretty similar. So that can account for this increasing boiling point. So the question is, why does water have the highest boiling point here? Why does water boil at 100 degrees Celsius when these boil less than 0? So the big solution here is the answer to this lesson. Water exhibits hydrogen bonding, which is the strongest form of intermolecular forces. So what makes it the strongest intermolecular force? Well, there's a couple things. First off, let's learn about when we have hydrogen bonding. First off, you need hydrogens bonded to fluorine, oxygen, or nitrogen. So you need to remember that F, O, and N all exhibit hydrogen bonds when bonded to hydrogen. But what makes those three elements so special? Well, if we look at their position on the periodic table, just draw a quick table here, they exhibit properties and are found in these spots, the top right, with fluorine being part of it. These are all incredibly or very electronegative. So they're very, very electronegative. So that means the dipole moment within water, or the dipole moment between HF, HO, or HN, these are going to be very large dipoles. So they all have very large dipole moments. But the thing is, we can get large dipole moments from a lot of things. So there's something else in particular. Specifically, one of the other aspects of why this is so strong is that hydrogen has no inner electrons. That means the electrons it shares, its shared electron specifically, is the only electron. And when it makes a bond with like hydrogen and fluorine, those electrons are so close, and hydrogen itself is purely just one proton. We have such a vast differential that this partial positive charge and this partial negative charge is almost very close to a full negative or a full positive and full negative charge. All the electrons that hydrogen has are closer to the other element. So this makes this one of the strongest dipoles that can exist. There's no electron repulsion happening within the hydrogen. So to clarify, just to make sure that we have this down, H bonds are the strongest IMF Just writing that again because it's very, very important. And it's between the partial negative or partial positive and partial negative charges of two molecules that exhibit H bonded to NO or F, or FO or N. And I made a mistake here. I said partial positive, partial negative. But this partial negative is actually going to be a non-bonding pair of electrons. So when we look at a hydrogen bond between maybe H bonded to an F and H2O, the hydrogen bond is specifically going to be between this partial positive and the partial negative, but between those non-bonding electrons and this hydrogen. So this specifically is our H bond. It's not a very important distinction, but one that might end up coming up within the DP exam. One of the other things that you should just generally know about H bonds is they are very common in bio or biochemistry. Whoops, can't spell that. Biochem. Very specifically, H bonds are what holds our DNA together. So they hold DNA strands together. So hydrogen bonds are very, very, very important for this type of chemistry and biology, as well as they're going to be used throughout the rest of our term as we learn about more different forces, more different ways that molecules can react and interact, as well as when we move into organic chemistry, hydrogen bonds are going to be very critical to this. So I hope this helps and have a great day.